We're finally ready. We've got all the terminology and all the tools that we're going to need to state what's called the fundamental theorem of Galois theory, which is really what we use over and over and over again as we study this subject area. Now, unfortunately, the proof of this theorem is rather complex, so we aren't going to get to the proof of this theorem. We won't have time for that, but we'll definitely be able to state it and evoke all of its beautiful power. So let's suppose that F is contained in E are both fields, and in fact, let's assume that this extension E is a Galois extension of F, and let's write G for the Galois group of E over F. Again, let's just define the sets script F, which is the set of all intermediate fields in between F and E, and let's let script G be the set of all subgroups of the group G. So I'm using again that less than or equal to notation for is a subgroup of G. Let's remember those maps that we defined when we were looking at the Galois connection back in the first set of slides here. So we had a map phi going from F, script F to script G, and we had a map theta going from script G to script F. And it turns out that if we had a Galois field extension, these maps theta and phi are inverse bijections of one another. So when we studied the Galois correspondence, we had these subgroup properties. We had 4 properties that we studied on that slide. The last 2 we had something along the lines of a field is a subset of the fixed field of the Galois group of E over that field. Here, it's no longer a subset. It's actually an equality. And it's not just, E being a Galois extension of F says that F is the fixed field of the Galois group of E over F, but in fact that's true of all intermediate fields, is what this theorem is asserting. So if we had a field K in between F and E, then K will be the fixed field of the Galois group of E over K. I'm saying that out loud so we understand a little bit better what these inverse bijections mean, but it's also important. You could try to talk yourself into looking at 2 different Galois extensions here. You could try to look at the Galois group of E over K or the Galois group of K over F. What this theorem is stating is that you will always have that K is the fixed field of the Galois group of E over K. It is not asserting that you will always have that F is the fixed field of the Galois group of K over F. It is not asserting that. That's something that we're going to see in these properties 1, 2, and 3. So it's just important that you read the theorem and understand it properly. But that is the statement that the maps phi and theta are inverse bijections. Now, furthermore, we can go even further than just saying that theta and phi are inverse bijections. What we can say is that if we pick a field K, an intermediate field K belonging to script F, and a subgroup H in script G that happen to correspond via this map, that is, H is phi of K, or conversely, K is theta of H, then we have the following things. First of all, the degree of the extension from K up to E, or the degree of the extension of E over K, however you want to say it, is equal to the size or the order of the subgroup H. And secondly, the degree of the extension from F up to K, or the degree of the extension K over F, is equal to the index of the subgroup H inside of G. So every now and again in the videos or in class you might hear me slip and say something like the index of F inside of K for field extensions. Part of the reason I'm saying that is I'm thinking of this theorem and how the degree of the extension of K over F corresponds to the degree to the index of H inside of G. And last but not least, I mentioned when I discussed that theta and phi are inverse bijections of one another, I discussed that that means that K is equal to the fixed field of the Galois group of E over K. We get the other direction that K is Galois over F if it happens to be the case, and in fact it's if and only if it is the case that H is a normal subgroup of G. So normal subgroups have always been sort of the most important subgroups of a group, and the most important subgroups of a group have this natural correspondence that Galois discovered with Galois field extensions. So in this particular case, it makes sense for us to say that K is Galois over F, and so it really is the case that F is the fixed field of the Galois group of K over F. And when we have the Galois group of K over F, it's going to be isomorphic to the factor group G mod H. And that factor group makes sense because in the case that we have this Galois extension, H is a normal subgroup, and we can look at the factor group. So really, really marvelous and powerful theorem, and hopefully in our homework we'll get to see lots and lots of applications of it. But since we're not going to prove it, let's do one example now to see how it helps us understand field extensions. So let's take a look at a particular field E. Let's let E be the rational numbers adjoin the square root of 2, the square root of 5, and the square root of 7. And let's show that this is a Galois extension of the rational numbers. And let's take a look at the Galois group of E over Q. And let's also use the fundamental theorem of Galois theory to take everything we know then about this group and draw it back to everything we can say about the field extension. So let's just study this as much as we can. First, let's show that E is Galois over the rational numbers. This follows fairly easily because we can see that E is the splitting field for the polynomial f of x, which is x squared minus 2 times x squared minus 5 times x squared minus 7. Certainly all of those polynomials split inside of the field E, and what we're going to discuss or figure out on our homework for this week is that there really isn't a smaller field in which this polynomial splits. In our homework we're going to show things like the square root of 5 does not belong to Q adjoin the square root of 2, that square root of 7 does not belong to Q adjoin the square root of 2 adjoin the square root of 5. So it is part of our homework that E is actually the splitting field for this polynomial and that nothing smaller will do. Now let's take a look at the field F2. Let's call F2 for the rationals adjoin the square root of 2. By this homework problem, in showing that the square root of 5 does not belong to the rationals adjoin the square root of 2, that's equivalent to saying that the minimal polynomial of the square root of 5 over this field F2 is the polynomial x squared minus 5. So if we then move up from the field F2 to a larger field by adjoining the square root of 5, so let's let F5 be F2 adjoin the square root of 5, then a similar argument that, again, will be done in our homework shows that the square root of 7 does not belong to F5. And again, this means that the minimal polynomial of the square root of 7 over the field F5 is the polynomial x squared minus 7. So if we move up from the field F5 by attaching the square root of 7, we'll be at our final destination of the field E. So E is F5 adjoin the square root of 7, and we can compute the degree of the extension from F up to E by multiplying the degrees of each of these intermediate field extensions from the rationals up to F2, from F2 to F5, and from F5 to F7, or I guess I didn't define F7, but E. And we'll multiply those degrees, which are each 2, by looking at these minimal polynomials, and we see that the degree of the field extension from E, of E over Q, is 8. So that's a good start. We know that we have a Galois field extension, so we know that the degree of that field extension is equal to the size of the Galois group. And so now let's take a look more closely at what this Galois group is. So on the previous slides we defined a field F5, which was Q adjoin the square root of 2 adjoin the square root of 5, and we can extend the identity map on that intermediate field F5 to a member of the Galois group of E over Q that sends the square root of 7 to negative square root of 7, one root of the polynomial to the other, extending the identity map on F5, so it's going to fix the square root of 5 and the square root of 2. In a similar way, we first went up to the field F5, which was Q adjoin the square root of 2 adjoin the square root of 5, but we could have traveled to another intermediate field. We could have gone up to Q adjoin the square root of 2 adjoin the square root of 7, and we could take the identity map on that field and extend it to a member of the Galois group of E over Q that sends square root of 5 to negative square root of 5. And similarly, we have another member of the Galois group of E over Q that's going to send the square root of 2 to negative square root of 2, and it's going to behave as the identity on Q adjoin the square root of 5 square root of 7. So note that each of these maps has order 2. You can undo them and have them be the identity map by just composing them with themselves. And so we have these 3 elements of order 2. And of course this is a group, the Galois group of E over Q, so we can start composing each of these maps with each other. So we could take the map that sends square root of 7 to negative square root of 7, we could compose it with the map that sends square root of 5 to negative square root of 5 to get a map that sends square root of 7 to negative square root of 7 and square root of 5 to negative square root of 5. And that's going to give me another member of the Galois group. And I have 3 different maps. I can compose them all sort of pairwise to to get these pairs of elements that are sending their square roots to their negatives and leaving one square root fixed. And then I could compose all three of them together and send square root 5, square root 7, and square root 2 all to their negatives. And all of those maps that I could create are going to have order 2. So what do I have? I've got the identity map, that's trivial. Then I get 4 other members of the Galois group of E over Q that are not the identity map, that send combinations of square root 5, square root 7, and square root 2 to their negatives. And then I have the original maps that just do these square roots to their negatives one at a time. Each one of those non-identity things has order 2, and that's a total of 8 maps, 8 members of the Galois group of E over Q. And we know by the fundamental theorem of Galois theory that if we have 8 things in the Galois group of E over Q, we have them all. So the degree of the field extension is equal to the order of the Galois group. So whatever this collection of maps is, it is the Galois group of E over Q. And what we have is a finite group with 8 things in it, each of which has order 2. And the only group with that property is Z2 plus Z2 plus Z2. So we conclude that the Galois group of E over Q is this finite abelian group Z2 plus Z2 plus Z2. But now we have even more information from determining what the Galois group of E over Q is. We have now determined that all subgroups, we have an abelian Galois group, so all subgroups are normal subgroups, which means that every single intermediate field in between the rationals and the field E is a Galois extension of the rationals. We deduce that there are exactly 8 intermediate fields, and each of them is Galois over Q. 8 intermediate fields because there's 8 subgroups of Z2 plus Z2 plus Z2. There are exactly 3 subgroups of Z2 plus Z2 plus Z2 of order 4, exactly 3 subgroups of order 2, and then you've got the whole group and you've got the trivial group. And this helps us to classify all the field extensions of the rationals that lie inside the field E. So 3 degree 2 field extensions, that's adjoining each of the roots individually, and then adjoining the roots pairwise, and those give you your field extensions of degree 4. And as we said before, each one of these is a Galois extension of the rationals. In summary, after studying these slides, and I say your textbook, although your textbook doesn't really cover much of what was covered in these slides, what do I want you to be able to do? So first of all, you should know the definitions of a normal field extension, a separable field extension, and a Galois field extension, and you should know how they relate to one another. Perhaps most importantly, you should understand equivalent conditions for normal, separable, and Galois field extensions so that you don't have to prove things using the definition. What you really want to be doing is proving that extensions are normal or separable or Galois using the equivalent conditions presented in these slides. The third thing is, we're not going to be able to prove the fundamental theorem of Galois theory, but we should really be comfortable with the statement of it, and we should know how to use it. In particular, you want to be a little bit cautious that you don't mix up the order of a Galois group with its index, and that you don't conclude in the wrong direction that an intermediate field is Galois over the ground field, when what you really mean is that the largest field is Galois over the middle intermediate field. And last but not least, you should be able to try to start using, as we did in the last example, the fundamental theorem of Galois theory to both better understand Galois field extensions and also better understand Galois groups.